We're going to look at Huffman coding. Huffman coding is a type of, as it calls it here, prefix code for lossless data compression. It was developed in 1952 at MIT by David Huffman. It produces a variable length code that can be used to compress files. So let's say I have the English alphabet, and I know how frequently each character occurs. Certain characters like the vowels A, E, I, O, and U are relatively frequent. Some characters are relatively infrequent, like X and so forth. What I would like now, in a regular encoding of text, each of those characters would take a byte. Actually, it's ASCII, probably only takes 7 bits, but we always encode it as a byte. So they each take the same amount of space, 7 bits or a byte, whichever way you want to look at it. It's normally a byte, of course. If I could develop a code such that the frequently occurring letters only had a few bits to represent them, and the infrequently occurring letters had more bits, and then recoded the text using this new encoding, the text would get smaller, and it would be optimally compressed, and it would be lossless because I could compress it and I could decompress it with no loss of information. They call it prefix code because any given letter, say like the code for E, is not the prefix for any other letter, say X. That makes it, of course, a great deal easier to decode. So if you're looking at a series of bits and you get to the point where you say, we got an E, you can be sure that that's an E, that it's not the prefix of an X. That there's not the initial bits are not the same as some other character. So that's important. It's extremely fast algorithm. If you sort the weights, it says you can get them down to linear, but of course sorting costs money too, costs time. It mentions it's not always optimal under certain situations, but it is fairly good. For the most part, this is what you want to use. All right, so what does it look like? Here is an example, not the best one, but nonetheless, it's an example. The white boxes are the data, and we have letters. And you notice they're not in alphabetic order. That's quite characteristic here. The tree will not be in alphabetic, well, it could accidentally be in alphabetic order, but normally they're not. So for each letter, we have a count, and that's the number of times it occurs, or a weight. However you derive that, I don't know. But you've observed text and you've counted the number of times all the letters occur. So the vowels, not surprisingly, a relatively high frequency. A blank is the highest frequency, and letters like R, P, X, U, and 1 in this collection are low frequency. So what we want to do is build a tree. You can see a tree has been built. Now, you'll notice that the low frequency data, letters, are furthest from the root, whereas the higher frequency characters are closer to the root. And this is the idea, because this can be translated into a binary code. If I say I want to encode the letter E, well, to get to E from the root, it involves going left, left, left. Now, if I say left is 0 and 1 is right, the code for the letter E would be 0, 0, 0. Alternatively, the code for the blank would be 1, 1, 1. The code for M would be 0, 1, 1, 1, and so forth. So that is where we are. So we get a binary code out of the resulting table. Question is, how do we build the table? How do we build the tree? Well, the way we do it, it's a relatively simple algorithm, is we initially start off with the tree isn't there, of course. It's just initially these boxes that are white. These are the original data. And we look across all the original data, and we find 2 boxes that gives us the smallest sum. The frequencies give us the smallest sum. Now, as it turns out, O and U would give us a 2. O and X would give us a 2. O and P would give us a 2. O and R would give us a 2. O and L would give us a 2. Any one of those would give us a 2. But it's also true that X and P gives a 2. There's a lot of combinations that could give us a 2. We don't care which one it is. just pick. If you've the first set you find that give you a 2, go with it. Now, since there's no other combination of weights that would give us a lower value than 2, we go with one of these. Doesn't matter which one. So we say O and U. We combine them together into an internal node with the weight of 2. Bingo. Then we look again and see what else we've got. Well, these guys are gone now. The O and U are no longer visible. They've been absorbed into the tree. And we say we get X and P. They give us a 2. And we'd say that R and L, they give us a 2. I'll just pick one of them. There's nothing less than 2. So we picked the X and the P. You could have picked X and R. You could have picked X and L. It wouldn't have mattered. You're still going to get a 2. So whatever gives you 2, you merge them together, and now you have an internal node with a 2. So at this point in time, what's left in the available nodes? Well, you've got E, you've got N, you've got 2. You don't see these guys. You got a 2 in place of them. You've got A, you got T, M, I. You don't see these guys. You've absorbed them. You see that one instead. So that's how we work. And so we then proceed to R and L, and we get a 2. Okay, now there's nothing else that's going to give us a sum of 2. So we look for the next lowest. And the next lowest sum would be 4. And there's a lot of possibilities that could give us a 4. Pick one. Well, let's go with the N and the internal node 2, which would give us a sum of 4. Great. Now, N, O, and U are no longer available. 4 is available in the tree. That's the only thing you can see now in the list of nodes. If these were a list, these guys would no longer be visible to the list. And then you pick T and M, and you get a 4, and you get I and this node here, and you get a 4, and H and S, and you get a 4. And, okay, there's nothing else that's going to give us a 4. So we look, go through the list and see what's the next highest combination. And it turns out to be this internal 2 with an F would give us a 5. All right. Now we go through it again and we say, well, what's the next one? Next one would be one of these sets of 8. The E plus the 4 would give us an 8. Could be. You could also say the E plus the plus this 4 too. It doesn't matter. You say, well, I'm rearranging the tree. We don't care. The tree is not alphabetic, so it's not intended. When we get down to the end, as you can see, it is not here. It's not intended to be in alphabetic order. Anyway, we keep doing this and keep absorbing until we finally get to the root of the tree, and the value is 36. Now we have a tree. We can traverse the tree and find out what these codes are. So if I start going through the tree, and I would come down here and I would say E is going to be 0, 0, 0. I would say that the next one would be N. That would be 0, 0, 1, 0. The next one would be 0, 0, 0, 0, 1. Excuse me. Let me go back. 0, 0, 1, 1, 0. I got off there. And 0, 0, 1, 1, 1, and so forth until we get a set of binary codes. So the binary code for an O is going to have 1, 2, 3, 4, 5 bits to it. The binary code for blank is going to have 1, 2, 3 bits to it. The binary code for E is going to have 1, 2, 3, the number of legs coming out of the root. And that's how we do it. All right. Can we do it with a program? Yes, we can. I have a program here. First of all, let's look at the data. The data doesn't have to be letters. Letters are fairly convenient because there's a small number of them, and you can put them onto a slide very easily. I have a file here of words that were taken from a collection of medical journal articles. These are some of the high-frequency words in a small collection of medical articles. And you see 3 columns. The first column is the number of documents, number of articles in which the word occurred. The second column is the number of times the word occurred in the collection as a whole. And the final column is the word itself. So we read that result occurred 278 times in the collection. It's 1,000 abstracts. occurred 278 times altogether in 215 articles. So result occurred in 215 articles, and in some of those articles it occurred more than once. Let's see the eyeballing here. The highest frequency appears to be group, which occurred 326 times in 135 articles. And so these are sorted by the first column. So the second column kind of bounces around. I think that was the highest for the second column was for group. But anyway, we're going to use the second column because that's the one that's got that's the real frequency of occurrence of these words. And what I want to do is come up with a bit code for each of these words. Then I want to re-encode the documents using this bit code. Now, you can see like the word treatment here has got 1, 2, 3, 4, 5, 6, 7, 8 characters. Now, when I finish doing this, it's going to come down to about a byte or more, something in the vicinity of a byte of bits. So the savings can be considerable. The savings, of course, are short word may have the length of the word doesn't tell us the length of the resulting code. The resulting code is going to be based on the frequency of the word, not the length of it. Looks like associate's a fairly good large word, demonstrates a large word. Some of these words are fairly long. Retrospective, relationship, I don't know, ventricular looks pretty big. Some of the medical words can get really large. They're not here because these are the high frequency ones. The large words tend to be lower frequency, investigation. So there's a word with the letter H. I don't know why that got in there, but nonetheless, it's there. It could have been hyphenated something, and the hyphen got dropped. So anyway, the result will be a bit code, and this is our input data. There are, as you notice down the bottom there, 980 lines. So there's 980 words to encode. All right, getting out of that. Here is well, if I'd spelled it correctly, it would come up. Here's the program. It's not a very long program. It's not super optimal, but it's a very fast program. So it works. It's a C program, so we've got some includes at the beginning, standard input-output, standard library, the string functions. Those are not uncommon. We have a node. The definition of a node, which is a structure here. The node consists of a string. This is where we're going to put the word, a frequency, which is the number of times the word occurs, a valid bit, telling me if the word is still available or this node is still available for recombination in the tree. If you noticed that once a word had been, or once a node had been combined, it's no longer available for combination. So this bit will basically tell me that. It's not a bit, it's an integer. It acts like a bit though. And then we have a bunch of pointers. Now this node is going to, at the same time, or nodes are going to appear in a list structure, which will be a list connecting all the nodes, both the original ones that were the result of words and the ones created. So we'll have a master list of all the nodes, and that's the next pointer, which will point to the next node in the list. And then we're going to have left and right pointers. That's for the tree. So we're going to be able to look at this node in two different data structures, one of which it's part of a list, and the other one is going to be part of a tree. So we have two separate, we have two classes of pointers, the left-right, which is the tree pointers, and next, which are the list pointers. Anyway, that does not declare an instance of node. It merely creates a layout. This creates an instance of a pointer. The pointer is called start, and it's capable of pointing at an instance of the structure node. This is a file pointer because we're going to write out a table at the end of all the words and the bit codes. We're also going to print the tree. The tree is kind of messy looking, but the table is what we really are. It's going to give us the words and the codes. Here is the print tree program, which we'll use at the very end. And it's a pretty standard print tree in that you come down, it's recursive. If there's a right pointer, you go down the right pointer. When you come back, that right pointer could take you down, down, down. But you've ultimately come back, you print the node that you were at before you went down to the, when you went down to the right side. And then you print the left side. The other decorations in here are for printing purposes, so I can print the thing in a decorative fashion, and also to put the zeros and the ones. Now, when I go to the right, I'm concatenating a 1 onto the string, as you notice here. Temp is going to be the is being created as the bit string that'll tell us the result, the number, the actual bit configuration. And on the other side down here, there's a 0 if I go to the left. So we add a 0 if we go to the left, we add a 1, we go to the right. We'll look at that later. All right, main program. Doesn't have too much in it. There's a string that'll be used to read in input, a couple of more or less utility integers, min, which will be looking for the minimum values. Of course, that's our integer that tells us. A bunch of pointers that are used as temporary pointers in the process of manipulating it. And M1 and M2, these are pointers all to type structure, that will be used to tell us which are the two current candidate minimum frequency nodes. As we go through the thing and we find a node, two nodes, the sum of whose frequency is lower than what we've seen otherwise, we will update M1 and M2 to point to them, and we'll make min point to or give the sum. So they are the current candidates for combination. Next of all, we got to read the data in, some decoration. Well, scanf not equal to end of file. Are going to read the lines in, and we're reading in an integer, another integer, and a string. And the new line tells us it's on one line. The ampersand is required because you have to send down the address of j and the address of I so that the scanf can actually put something into them. We don't want to send down the value of I and j. And then C. Well, C is the name of the character array, character string. Therefore, it already is a pointer. So you don't send the ampersand C, you send C. C, because it's the name of an array, it is a pointer. Well, it's not equal to end of file. I write out, echo to the output what I got. There's the string I read in, that would be the word, and D, which is I, which is the second column here, as you say. That's the one I'm interested in, so I print it out. I create a node. Malloc is how you allocate data in C, memory allocate. You have to tell it how much data to allocate. Well, size of one of these nodes, size of the structure node. So that'll allocate sufficient space for a node. Malloc comes back as a pointer to void. You have to modify that to calm the compiler. Pointers are really all the same, but the compiler sees pointer to void being assigned to pointer to node, and it says what? Oh, we don't want it to say what. So we have a cast here, casting the pointer to void to pointer to to node. Excuse me, it's hay fever season here. If P1 comes back as null, it means we ran out of memory and we abort, which is unlikely, but it's possible. You could get in the loop. All right, we make P1 arrow next point to start. Well, initially start is null. You notice up here we did set it to null. So if this is the first node, its next is null. We make start point to it. We are going to be adding items to the front of the list. We make left and right null. We copy the string into the node. P1 arrow val is the string area of the node. We set the frequency equal to I, and we set valid equal to 1. Yes, it's valid. All right. Then we go up and read the next one. Well, the next one, we make the next one's next point to start. Well, start is pointing at the one we just read in, so now it becomes the second one, and this one where we just created becomes the first one, and so we're adding at the front of the list. When we're all done, we print out some more decoration, and we're ready to go. What we need to do is we need to start running through the nodes, and I'm just calling them A, B, and C. And for node A, it's either one of the word nodes or one of the internal nodes. It doesn't matter. We want to compare it with node B, C, D, E, F, whatever, and find out who's least. who is the smallest sum. And then we want to move to node B and compare it with C, D, E, and F, and so forth. And then we want to go in a line that's not shown here. We want to go start with C and go C with D, C with E, and so forth down the line until we've completed this process, where every node has been compared with every other node. I can start with B and compare it with C. I don't have to compare B with A because I've already done that. A with B is the same as B with A. Then the value of the sum is going to be identical. So each time through it's a little bit less work. But I keep doing this until I've exhausted all the possibilities. And that's basically a pass to find a pair of nodes that I can combine together. I want to find two nodes to combine together. I have to exhaustively do this until I got them. Once you've got two nodes, you know their minimum, you create a new node, you combine them together, you put it into the tree, you make the two nodes that you used invalid so they won't be recombined again because they're still in the list. We're not deleting them from the list, we're leaving them there. We're going to need them later. But that's the process of finding a pair of nodes to combine. All right. What do you do then? Well, we keep repeating this process until there are no more possible nodes to combine, until we get a tree with a root. So we've got actually we're going to have three levels of loop here. We're going to have the outermost loop, which is what's starting next, which is a loop forever. And it is going to start at the top of the, it's going to start and it is going to keep repeating until there are no more nodes that can be combined. And I suppose the easiest thing, go right down to the bottom here and find the end of it. And this is the end of it here. This is for this guy right here, this while here, let's look at the end of it. Repeat until all node sums are computed, it says. And I'll leave that there, and we'll just go down here and see where it pops up. Now we're at the same level here. Prior to this point here, we actually are combining the nodes. That's where the nodes get combined, and you see there's the valids being set to 0. Worry about that later. But this is the question right here as to whether or not we're going to repeat the loop. Repeat that outer loop or not. We set I to 0. We go through the list. That's going through the list. We skip it a node if it's not valid. In other words, it's already been accounted for. Otherwise, we increment I. Okay? And when we come out, if I is greater than 1, we continue. The loop does it again. Why? It means we've got more than one node. We've got at least two nodes that are still valid. They haven't been incorporated into the tree, and we need to go find them. If I is 1, then the tree's done. We've got one node. If I is 0, we got a problem. I hope that doesn't occur. It doesn't. So if I is greater than 1, it means we've got at least two nodes that are not yet accommodated. They're not yet absorbed into the tree. That's important. And this is just a simple run through the list, skipping nodes that are not valid. Nodes that are valid cause I to increment. And we get down here, we say, what's the value in I? If I is greater than 1, yeah, there we go. There's at least two nodes up there to be combined. We're going to go find them. Otherwise, we break. And that takes us to done. All right, that's the outer loop. There's the outer loop. The outer loop starts with start. P1 is set to start. Min is set to -1, because we have got no min now. We're going to have to find one. Now we've got some internal whiles. We've got this while here, and you notice we've got this while down here. The outer while is going to run on the P1. That's the first node in the pair that we're comparing. So this node, this while it begins here, would correspond to looking at the A. A would be the P1, and then it would move to B, and then it would move to C. And okay, the inner loop is going the B, C, D, E, C, D, E. It's the other item in the pair. So the outer loop selects the first item in the pair. This inner loop here selects the second item in the pair. So P1 starts with start. If P1 is not valid, then we advance to the next one. If P1 turns out to be null, well, we break. And that takes us out of this internal loop, and we drop down there, and and that means we've completed a pass. And then we do the stuff at the bottom of this loop and determine whether or not we want to do the outer loop again. So this means here, when we break out of here, it's one of the possible break places. Well, actually, this is technically the break down here. If P1 is equal to null, we break, and then P1 equal to null, we break. This is the break right here, which actually kills off this while. All right. So if we get to here, get beyond this point, we have a P1. We have a valid node that has not been absorbed into the tree, and we're ready to compare. And we find a candidate P2. P2 will be, we start with the first node following P1, which may or may not be valid. I don't know. We'll find out very soon. But P1 is now fixed. We enter into the inner loop here. The inner loop is going to play with the second node in each of these combinations. And we ask the question, is P2 equal to null? Well, if P2 is equal to null, it means the inner loop has nowhere to go. Means that P1 is already down to the end of the list, and there are no more P2s to compare P1 with. So we're out. And that recycles us back to the outer loop here, which there may be another P1. I'm just saying that the first P2 is the one that's immediately following P1. But in the course of this thing, P2 is going to cycle. Eventually, P2 will get to the end of the list itself, in which case we break and we decide whether or not we want to repeat the outer loop. Okay, so if we get to this next line here, we know that P2 is not null, and we ask, so long as while it's not valid, in other words, if P2 is valid, we don't enter this while. If P2 is not valid, we advance it, and we check to see if it's null. If it is null, we break, and then we have this second break here because of structured programming. That breaks us out of the outer loop here. This inner break here only breaks us out of this loop. This break here breaks us out of this loop. So no more nodes to test. We're done with all the P2s at that point. That's the exit for P2. It's one of the ways. Two ways of getting out of here. There's also this one up here, which could have happened. Well, this P2 that we found here could have been null, and that would have taken us out. All right. So now we get down to actually looking at the sum. Special case. If min is equal to -1, it means, at least for this pass, we have not found we've not done any sums yet. So whatever it is, it's the minimum. It's the only one we've seen so far. So we set min equal to the sum of frequency from P1 and the frequency from P2. Then we go to, and we set the pointers, M1 equal to P1, M2 equal to P2. We remember which two they are. Otherwise, which would be the much more common case, we ask if the sum of the frequencies is less than our current min. If they are, we update min to be the new sum, and we remember P2 and P1 in the form of M2 and M1. All right, and then we advance to the next P2, and we recycle the loop. So this loop is right here. This is the inner loop, which is comparing the set of P2s with P1. Now, of course, in this process of advancing here, when we go back up, first thing we do is check to see if it's null. If it's null, of course, that means there's no more P2s out there. And we, and in the process of exiting, this area down here is the follow-on of this part of the loop. So when we exit the inner loop, there's your inner loop. Here is our outer loop here. The inner loop comes out here. We ask, is there any more P1s? If P1 arrow next is not equal to null, we update P1 and we continue. The continue, of course, is for this while. So this while recycles. So in other words, when we exit the inner loop, we ask the question, are there any more P1s? And if there are, if P1 arrow next is not null, we update P1 and we do a continue, which takes us right back up here, and then we start checking valid. And the fact we get a P1 doesn't mean it's anything we can combine. But when we get up to the top of the loop, we'll go through here and check to see if it's valid. And that could exit us out also. That would exit us out to the outer loop, the further outer loop, which this does here. If the next P1 is null, it means we've finished one of these inner passes that we've taken for some A, we've combined it with all B, C, D, and E, and we've got a sum. So we got a candidate. We got M1 and M2 are pointing at nodes. And they are pointing at nodes whose sum was the least for this pass of those valid nodes. Remember, we're always skipping the invalid nodes. All right. And as soon as we get out, and here's where we get out, we print out for this pass, the sum is D, % D, which will be min, for nodes blah and blah. And you see min is going to be printed out through the % D, and the string associated with M1 and the strings associated with M2 are being printed out there. So we will see, flash by, what each pass found as a min and what the words were. Now, as it turns out, internal nodes don't have any words, and in place of the val on internal nodes, I replace it with an asterisk. All right, we're ready to create. We allocate as before memory. I check to see if it's came back null, and we add this new node onto the list. This is the internal node that we are creating. It added to the front. It points to start, then start points to it, so it's being added to the front. Its left is M1 and its right is M2. Those are the two subnodes whose combination gave us the least value. Whose sum gave us the least value. So the left and right nodes are M1 and M2, which could be leaf nodes or they could be internal nodes. I don't know. I can't tell from here. We do know this is an internal node, and it does not have a word associated with it. So I just copy an asterisk in. You can copy anything in what you want, just you have a placeholder. So the frequency is min, and the valid is equal to yes. It is a valid node. All right, and then we set the valid int marker for M1 and M2 goes to 0. These two nodes represented by M1 and M2 are no longer available. They are they've been absorbed into the tree. Then, as I said before, we go through the count. We go through the list. This loop here is a fairly quick way of going through the list. We start at start. As long as P1 is unequal to null, we advance it to next and so forth. And if it's not valid, we just move on to the next one. If it is valid, we increment I. When we out of the loop, if I is greater than 1, it means we've at least two nodes left in the tree and they can be combined. If it's 1, there's only one node, we're done. All right, when we're done, we come down here and let's see. This here, I have no idea why that code is in here. It is we're going through the whole thing, and I'm looking for starting point. Didn't recognize that. The first node in the list may not be was probably not the root of the tree. Think about that. It's the start of the list. It's not the top of the tree. Could be. So where is the start of the tree? Where is the root of the tree? Well, there's one root, and it's in the list. And it's the only one in the list which is still valid. All the other nodes have been absorbed. So there should be, at this point in time, only one node in the list which is valid. That's the root of the tree. It's not start. Could be, but it's not. So I didn't notice what I was doing there. But anyway, so I go through the list looking for, as soon as I find something that's valid, break, because there's only one node in the tree. We found it. And that is the one we're going to call tree print with. I open the file F1, and I call it codes.txt. It's open for write. Then I call print tree, and I pass to print tree P1, which is the pointer to the root of the tree. I pass down I, which is set to 0 initially, which is basically going to be incremented each recursive call to print tree to tell us how far to indent when we print out the tree or attempt to print out the tree. And we start off with a code of empty. This is where this third parameter here is where the binary code associated with the word is going to accumulate. When we come back from print tree, we have printed the entire tree, and we have also written out all the codes. So we close the file. Now going back up to print tree, here is print tree again. You can see it receives a pointer to the node, and I is an integer, and the path. And we've got some characters here. I copy the path, the current path that we have into code, and I also copy it into temp. Okay, when I go to the right, I concatenate onto temp a 1. So whatever came down as path, it's in temp. And I am going to concatenate a 1 onto the end. Why? Because I'm going to the right. And I'm just arbitrarily said going to the right means 1. You can flip that and make it 0. But that's a little more traditional. All right, so I call down print tree. It's a recursive call. And and you notice these are all automatic data types, so that they'll be recreated on each entry. I call it. I'm giving it the right pointer. Right pointer is not null, so it's a good valid pointer. I increment I, which means this is going to be a depth counter. How deep are we? And temp. Well, temp has at least a 1 in it. Could have quite a bit, but the last character in it is a 1. That prints the right tree. When I return, I'm indenting. I'm going to actually print out the node here. From 0 to j less than 1, so if j is if I is 5, I'm going to loop 5 times. And I just arbitrarily pick, what have I got there? 1, 2, 3, 4, 5, 6 blanks. All right, that's an indentation. You can play with that, but it's an indentation for before I print. And then I print out in parentheses the value. Many of them, the internal nodes will all be star. The frequency, the accumulated frequency for this node, and the code that we've got. Now the code is path. When we originally came in up here, we copied path into code. All right, we preserved it. We also copied it into temp because that's going to get messed up. We've already messed it up. We put a 1 onto the end of it. Code is the original value we came in with. That is the actual code for this node. And we print it out. That'll be the binary code. If it's an asterisk, which means it's an internal node, I print things out slightly differently. So what did I? Oh no, excuse me. If it's an internal node, I print out the. Let me get this straight again. I'm reading it wrong. If it's not an internal node, I didn't miss the not equals. String comp compares 2 strings. If they're equal, the value is 0. If they're not equal, the value is not 0. So if it's not 0, then I am going to print out to this codes.txt. That's F1. There's the file pointer. And what I'm printing out is in a field of width 5, the frequency. In a field of width 16, right justified, I am going to print out the text, which is the value stored. And 16 turned out to be enough, I think, to hold all the words. and then excuse me, that's the code. The code goes out in through this one. Then finally the word itself. So I'm going to that leaves up to 16 bits, which was 16 characters for the bits, and that's more than enough. The left side is pretty much the same. However, I copy from path back into temp. Path is still the same at this point. We haven't modified path. So at this level of the recursion, it'll still be the same. And then instead of concatenating a 1 onto it, I concatenate a 0, and we print the left side. So there it is. Sorry for a couple of flubs there. All right, and compiled it, and it's a dot out. So it's a dot out, and it's term freak dot text is the input, and term frequency dot text. Did I get that right? Yeah, frequencies. I think that's the way it's spelled. It's going to flash by very quickly, and there it was. What it did. Let me run it again. This time with more. Run the output to more. There's the input coming in. Step through. And here are the passes that I mentioned before. For this pass, the minimum sum is 27 with accumulate and significance. Those are the two words it picked up. And now you see eventually it starts getting asterisks, which means it's combining internal nodes. And as we get further down, there'll be more and more internal nodes combined until finally there's just almost nothing but. And here is the attempted tree to print out. And let's see if we can find a place in the tree. Well, let's see. We've got node with the weight of 236, and it has 1, 2, 3, 4, 5, 6, 7 ones, which means it's all the way to the right. Ventricular has 1, 2, 3, 4, 5, 6, 7, 8 ones. So the code for ventricular is 8 ones. On the other side of that would be the node with 118. It has 1, 2, 3, 4, 5, 6, 7 ones and a 0. That's the left going. The left going node of 236, which it's not, that's the number, let's just call it 236 node, is to 118. Its right node is this guy with a 1 at the end of it, and that's the word exposure. On the left side is diet with that combination, but it's got a 0. This one has a 1, this one has a 0. The difference in the length, of course, is due to the, I should probably maybe have made that a constant value, but it's due to the difference in the word exposure and diet. But that's how the tree looks, and you see the tree gets deeper and deeper and deeper. And someplace in here is the root of the tree. That might be it right there. Yeah, that's it, right? That was it there. Yeah, because it, well, it's got a 1. So that's the first one going to the right. I don't know where the root of the tree is here. It's in here. So there it is. There's the root of the tree. It doesn't have a binary code because you haven't gone anywhere. You haven't gone left or right. There is the root of the tree, and the master sum is 41,387. All right, let's get out of here. We also built this thing called codes.txt. There they are. You can see the original frequency is the first column. So ventricular had a frequency of 118. There's the bit code for ventricular. And these are coming out in order. This is coming out the way the tree was printed. As we traversed through the tree, left, right, all that sort of thing, these words got printed out. This is not, they're not sorted yet. So you can see there's different length bit strings. Let's sort them by frequency. Sort -nr, which is numeric sort. I want to sort on the first column. Reverse order, so the highest will come out first. And it would be codes dot text, and I'll just send them out to a file called XXX. There they are. Group was the highest frequency word, and you see it has a 1, 2, 3, 4, 5, 6, 7-bit code. So you could represent the word group with a 7-bit code. We get to 8-bit codes when we get to active, and you see we go further down, the length of the codes get greater until we get to the bottom down here, the ones that occurred with a frequency of 10 and fewer, or slightly more. And this is a 1, 2, 3, 4, 4, 8, 12-bit code. So it varies from 7-bit codes to 12-bit codes. These codes could be used to replace the words in the original text, and the text would be a lot shorter. Now, I wouldn't, even if I replaced them as characters, it'd probably be shorter in, I guess, not all cases, but since they represent bits, it means that a word could be represented in slightly less than a byte, up to a byte and a half. And if we pack them all together, we will have compressed the original text considerably. Now, how do you encode things? Well, since the tree is not alphabetic, you can't go searching the tree. There's no way to search the tree. So you have to have a table, a lookup table. So if you get the word white, which is on the top there, you'd have to look up in the table and find out what the code for white is, and then pack it into your output. On the reverse, if you've got something that's encoded, and let's say white is the first word, you would start. Now you could use the tree, because you would start at the root, and 0 would tell you to go to the left, next 0 tell you to go to the left, then a bunch of 1s tell you to the right, a bunch of 0s tell you to the left, and you keep zigzagging through the tree, because this is actually the description of how to get through the tree. You'd find white at the end of it. White is not the prefix of anything else. It is the code itself. There is no other code with that prefix, and it would take you there. You could also use a lookup table, but you could use the original tree in order to decode, and that's, of course, pretty quick, because it's essentially a binary lookup at that point. I guess if you had a table, you could do a binary lookup on a table, but either way, with the binary lookup that you found it when you reach the end of the tree, when you reach the leaf on the tree, because there will be no descendants. It's unambiguous when you get to the end. So that's Huffman coding. I'm going to look at a couple of others. I'll put the code in the comments. If not there, I'll put it on my website.